I will be talking about the quest for Venus quakes. And this is very much work that has been done with a whole team, a whole bunch of people. We had a few meetings, and yeah, you can see all the names here. But yeah, well, what Julia kind of referred to before this, and what David in the next talk will definitely be talking about, is volcanism on Venus. And this is from a paper in 2023. Becca Hahn mapped a lot of the volcanoes and volcanic units on Venus. And as you can see, this is a map. There is a lot of volcanoes on Venus. It's a very volcanic planet. And recently, in the last couple of years, we've also had indications by reanalyzing Magellan data that some of these volcanoes might actually still be active and have active lava flows, which again I'm sure David will talk about at length in the next talk. This is all to say there is, or at least definitely was, maybe is, volcanism on Venus. And we know that on Earth, if we have a volcanic eruption, that goes paired with some kind of tremors, some kind of seismicity. Now, if you pair that with the fact that this is another map of Venus, you see lots of different tectonic structures on the surface of Venus. You see these massive rift belts here illustrated in orange. You see the coronae, which are these round kind of features that may or may not be active. We see massive mountains. And again, we know on Earth that these kinds of settings are very tectonically and seismically active. So the question that then pops into my head, and hopefully also in yours, is, well, if that is all true, could there be quakes on Venus? Because we could learn a lot from quakes on Venus. Like, studying the seismicity of Earth has taught us so much about the interior. So, are there quakes on Venus? Can we use them somehow to learn more about Venus's interior? Well, first we need to consider this from a theoretical standpoint. Like, is it physically possible that there are quakes on Venus? And the kind of trouble there is that Venus is a very hot planet. And in order for there to be earthquakes, you need to have usually a shallow layer in the crust or lithosphere of a planet that can behave brittly. And that is usually associated with cold temperatures. Venus is of course very hot, surface temperature of 460 degrees Celsius. So the question is, can there actually be some brittle deformation that would facilitate quakes? So in order to answer that question, we need to look at the seismogenic thickness of Venus. And the seismogenic thickness is the upper layer of a planet that can behave in this brittle manner and where earthquakes can nucleate. Now, one of my colleagues, Julia Maya, has looked at various different ways of trying to estimate the seismogenic thickness of Venus, and I very quickly want to go through them. If you have more questions about this, please ask them later. But there are many different ways because we don't have any direct constraints. So the first one is looking at flexure. So if you have a load on the surface, it can deflect the lithosphere. And from this, you can in very basic terms, get the elastic thickness, the mechanical thickness. And if you continue on that and make quite a few assumptions in the process, you can get the thermal gradient. Now, lots of people have already studied the elastic thickness and the flexure of different tectonic structures on Venus, and sometimes also even derived a thermal structure from that. What we now did is translate that to seismogenic thickness, because as I said, on Earth, we know that where you can nucleate earthquakes is kind of associated, very roughly correlated at least, with temperature. And if we look at the oceanic lithosphere and the thermal models we have for the oceanic lithosphere on Earth, we can see that where you have quakes nucleating, the epicenter of quakes, the hypocenter of quakes, you can see that they very roughly kind of follow the 600 degrees Celsius isotherm. So that is more or less the approximation that we use here to look at where the 600 degrees Celsius isotherm is to say what the thickness is of the seismogenic layer. Now, if we do that for these flexural studies, which got the thermal structure, then we get these kinds of seismogenic thicknesses. So, from very, very thin to up to 40 in the, largest case. Another way of looking at this, in order to have some kind of sense of what the temperature distribution is inside the planet, is looking at geodynamic models and running thermal evolution of the planet and seeing what happens. So in order to do that, of course, it's all dependent on your input. So the way we go about that is we try different things. Here I present two different ways of thinking how the interior of Venus works. Either you have extrusive magnetism, which means that everything that melts in the interior gets put on top of the planet and then immediately cools, or you can also have a percentage of intrusive magnetism. So everything that is melted, some of it is put on top, some of it is put at the base of the crust. Depending on, which one you choose, you get very different thermal structures throughout the lithosphere. And this then translates to very different seismogenic thicknesses, because again, the depth of the 600 degrees Celsius isotherm will change. So you get these kinds of end member scenarios where one is 100% extrusive, which results in this very thick isolating layer where you have a very deep 600 degrees Celsius isotherm. Or you say, well, no, there's also a lot of intrusions, just below the crust, and then you keep more or less like lower seismogenic thicknesses. The 600 degrees Celsius isotherm is not as deep. And of course, nature is nuanced, so it's never going to be 100% extrusive, and 20% extrusive volcanism is probably more kind of what we expect it to be. So that is what we think is the most reasonable. As the last way of looking at the seismogenic thickness of Venus, we looked at mantle density anomalies. We have the long wavelength gravity and topography from Venus. And from that, you can get density anomalies. And if you then make assumptions on like a reference temperature and reference depths of the lithosphere, you can translate that to temperature anomalies and therefore again seismogenic thickness. And then the map looks like this. So we've seen lots of different maps now, and they say lots of different things, but this is just to see from different perspectives what the seismogenic thickness could be. To kind of see whether they all make sense and point towards the same direction, we also plotted it into one plot. So here we see the seismogenic thickness for the three different methods: lithospheric flexure, geodynamic models, mantle density anomalies. And we plotted all the points we had, and you can see, this outlier here at the top is the 100% extrusive case, which we don't think is very realistic, but otherwise they kind of are all in the same ballpark, between around 2 kilometers and 35 kilometers depth or thickness of a seismogenic layer, with a median of 24 kilometers and a mean of 23 kilometers. This all to say that this means there is a good indication that the seismogenic thickness of Venus is not zero, meaning there could be earthquakes. So that is very exciting. And if, from this physical perspective and the anticipated temperature structure of Venus, we then say, okay, there is probably a layer that can produce and host earthquakes. The question naturally becomes, how many quakes would we expect then? Because, those are the kind of things you need to know if you want to have a mission and, if you expect anything to be recorded at all, or if it's so low that you would never be able to measure it. So in order to kind of get an idea of this, we thought, it's difficult to figure out for Venus because we don't know that much. There is, no data we can really look at the moment to answer this question. But there is one planet where we know a lot about seismicity, and that is our own lovely Earth. We know so much about the seismicity of Earth, and, as discussed by Julia, Venus and Earth do have some similarities. We don't know why Venus is so different, but perhaps if we want to study Venus, we can take Earth as a reference and then try and morph it into what we think Venus is to see what would happen. So what we're going to do is we're going to scale the seismicity of the Earth to Venus to get an idea of how much seismicity you would expect if some of the processes work the same on these two planets. So for that we have this map of the Earth, and we divide it in the tectonic settings of the Earth, which we know very well. And we know the areas of all these settings. And so we have them all beautifully color-coded. What we also have is a catalog of seismicity. We've recorded the seismicity of Earth. This is all known. So what we can do is we can add the seismicity that we know of Earth on top of this, and then sort it automatically into the tectonic regions, the tectonic settings that this seismicity is associated with. That is what you see here. Beautiful. Now, in order to kind of get an idea of the different numbers that are associated with this, what we can do is we can plot it in just a normal graph. And so here you see on the x-axis the seismic moment, or the moment magnitude, so the size of the quake. And on the y-axis you see the number of quakes per year that have that magnitude or are larger than that. So this is for the Earth. You see I've dashed an Earth seismicity reference line because that dark blue line that you see, the solid one, is all of the seismicity of the Earth combined. Then, as you would expect, most of the seismicity of the Earth, if you split it out, is from subduction zones. There is just a lot of seismicity at subduction zones, and you see that here in the pink line. And then if you go a bit lower in the graph, you see all these other colors, and they represent the other tectonic settings. Now, this is a great graph, but it is kind of unfair to compare it like this, because as we saw on the map, some regions are much larger than others. Like the amount of oceanic lithosphere is much bigger than the area of strike-slip faults, for example. So in order to get a good estimate of the seismic signature of different tectonic settings on Earth, we need to divide these numbers, these lines here, by the area of the different tectonic settings, of the relevant tectonic settings. So if we do that, we get the number of quakes per year per square kilometer. And then you see, again, subduction is the highest. Just whatever way you look at it, the most seismicity is happening at subduction. Then you see a little bit below that all the different plate boundaries and the global Earth measurement. You have the seismic signatures, and then if you go much lower than that, in these like light blue colors, you get the intraplate seismicity, so intracontinental and intraoceanic, because there's not that much seismicity there. It's not an active plate boundary. So this is very interesting, and what we can do now, as we have these seismic signatures, and so kind of the rate of quakes per year per square kilometer for these tectonic settings on Earth, we can look at analogous quakes, like analogous tectonic settings on Venus, and see, because we know what the area of these different tectonic structures that we see on Venus is, and then kind of estimate how much seismicity there would be expected with that. Before we do that, because then we scale by area, what we also need to do is scale by volume, actually. So we need to consider the depth, aka the seismogenic thickness I've told you about earlier, in order to see how you scale from Earth to Venus. So we just had this, this beautiful work in progress from Julia Maya, which I showed with the 3 different estimates of seismogenic thickness. But for this exercise of going from Earth to Venus, we actually took a much simpler approach. This is not the main thing of this particular topic. So what we did here is we looked at Earth's average seismogenic thickness. We calculated that using some rough estimates to get an idea, and we got to about 27 kilometers. And then we wanted to get a range of the possible seismicity of Venus. So we looked at what would be the absolute minimum seismogenic thickness we could expect on Venus, which turns out is at rifts, because there, you expect to have a very hot environment, so the 600 degrees Celsius isotherm should not be that deep. So we found out about 7 kilometers, and then the maximum kind of that we use here aligns with what Julia Maya found in what I showed you earlier, which is about 23 kilometers for the maximum seismogenic thickness. Which aligns with her average estimate of seismogenic thickness globally. So we take these two end members, 7 and 23, and compare it to the 27 of Earth in order to get this range of what kind of seismicity we could expect. So then we have 3 different end member estimates of how much seismicity we could expect. First, we say that the entirety of Venus is kind of inactive and therefore has the same seismic signature as Earth's continental intraplate seismicity. Now, if we do that, we have the dashed reference line from Earth, but the range you see is what we see for Venus, and we get a few hundred quakes of magnitude 4 or higher per Earth year on Venus. But we don't think Venus is inactive, so this is the absolute lower bound of what we would expect. We actually think Venus might be active, and at least some of the tectonic structures as well. So for that, we then make a realistic active estimate, where we say that a subset of the coronae are active and have the signature, the seismic signature of Earth's subduction. The ridges and mountains on Venus have the seismic signature of Earth's collision zones. The rifts on Venus have the seismic signature of Earth's continental rifts, and the rest of Venus is again this Earth's continental intraplate. And then you have all these different seismicity contributions that you add up in this dashed area here. And then you get a few thousand quakes, magnitude 4 or higher, on Venus in an Earth year. Now, we can also go crazy and say, well, we think everything that could be active is definitely active. And if you do that, then of course the amount of seismicity you would expect on Venus increases. You get many thousands of quakes expected per year with a magnitude 4 or higher. And you kind of at the upper limit are at the same level as the seismicity of the Earth. As you can see, it overlaps with the dashed line. So if we put this into perspective, you see here the 3 different global estimates: inactive in gray, active, realistic and light green, and then active, crazy active in dark green. You see what kind of seismicity we would expect. And as I said, the most realistic one is the realistic conservative active one in the middle, that middle line. So now we have some kind of estimate of how much seismicity we expect on Venus, thanks to looking at the Earth, which is very cool. But the natural question then, of course, is to ask, could we detect these quakes on Venus to get some kind of knowledge about the interior? Well, there are many different ways to potentially detect quakes on Venus, because the missions that are going now that have been selected, like Envision, as we've just heard, they can look at surface changes, perhaps, but they can't explicitly look at seismicity. They can't detect seismic waves, so we can't then use the information in seismic waves and patterns to learn anything about the interior. So the current missions that have been selected and are going definitely to Venus, they can't really help with this. So we need to look at the next mission. What could we do in order to detect quakes on Venus? Well, different options. Someone just asked about a lander. So a lander would be great. There's also the option for a balloon, or we stay in orbit. And I'll go through them very quickly. So first, you could have a broadband seismometer, which you would place on the surface. They are the seismometers we have here on Earth. They are very sensitive, excellent, great. The only downside is that since Venus is so hot, it probably won't survive long, which is a problem. Plus, it would be very difficult to power it because there's no sunlight reaching the surface. So how do you power the thing? And also the data upload rate would be very much constrained. So there are all kinds of technical reasons why a lander is very difficult at the moment. Having said that, it would give us the best measurement of seismicity, if this would be possible. So in order to kind of see that, I want to explain this graph to you, which I've had trouble with, but I will explain what it means. So what you see here on the y-axis is the minimum number of events per year, Earth year, that you would need to detect one quake of a certain magnitude. And then the different lines you see are for different signal to noise ratios. So if there is very little noise, you're looking at the graph that is the most sensitive towards the left. You have this flattening of the curve because at some point a broadband seismometer has like a magnitude 4 point something. As if that happens anywhere on the planet, a broadband seismometer is sensitive enough that it can actually pick it up. So your constraint of how many events per year you need is, well, if your seismometer is gonna survive for one day, you need one quake a day, and then you will measure something during your mission duration. That is how this graph works. But as I said, practically speaking, very difficult to do. Probably not going to happen a seismometer. Now, the other option is a pressure sensor on a balloon, because the atmosphere of Venus is very big and therefore dense at the surface, so it's very well coupled to the surface. So if you have seismic waves traveling through the solid planet, they can then continue propagating in the atmosphere as gravity waves, sound waves, all kinds of things. And you can measure that with a pressure sensor on a balloon. And if you do that, you need less quakes per year, but you are limited, as you can see immediately, to bigger quakes. Like you need a big one in order to get enough, like a good enough signal in the atmosphere so that a balloon can pick it up. Lastly, what you can do is looking at air glow. So in the upper atmosphere, because there is sunlight falling onto the upper atmosphere, you have ionization, which emit an air glow. And you can see the wave patterns in this air glow from an orbiter that is very far away and looking at the disk of Venus. And that is also a way in which you can, measure, detect seismic waves and patterns. If you do that, you can see the minimum number of events per year you need to measure one quake goes down drastically and becomes quite realistic. But again, you're much more biased towards big magnitude quakes. So just a brief summary here. You can see the solid lines are the detection capabilities of the different methods I just showed, and then in the background we see the different estimates of seismicity. And as you can see, if we think that the active conservative estimate is correct, the orange one, we need either a balloon or probably the air glow imager is the most relevant. And partly the reason why it's most relevant is because it has a very long mission duration. An orbiter can stay alive for very long, like 2 years. So there is a lot of possibility to measure something. So just to sum up, in terms of estimates of seismicity, an inactive Venus, if you want to believe it's inactive, you are looking at a few hundred quakes of magnitude 4 per year or higher. If you look at the most realistic scenario, where some of the tectonic structures we see at the surface are at the moment tectonically active, there's a few thousand quakes magnitude 4 or higher annually. And if you go super crazy and think that everything is active, you get many thousands of Venus quakes magnitude 4 or higher. In order to detect these quakes that may or may not be there, airglow images are at the moment the most promising because they can, actually have a mission duration of about 2 years. So you have the highest chance to detect Venus quakes and learn something about the interior and tectonics of Venus in the process. That was it. Thank you.
Thank you so much, Iris, for the presentation. Super clear. There are a couple of questions in the Q&A section. I'll read them to you. So the first one is it possible to find raylight or even some love-type seismic waves on Venus?
Sorry, somewhat?
Is it possible to find raylight or even some love-type seismic waves on Venus?
Oh, different types of seismic waves. Yes. Yes. So I think, if I'm correct, that the airglow imagers would actually measure Rayleigh waves. So actually, they're measuring mostly surface waves because they can propagate in the atmosphere, and probably you can get different waves as well. But what I've heard, mostly people, in terms of realistic detection capabilities, are looking at radio waves and sound waves, infrasound, that kind of area. So if you want to look at body waves, this is why everything I showed was in surface magnitudes and stuff. You would need a proper seismometer, broadband seismometer for that, I think.
Okay, thank you. The second one is, can interferometry help detect Venus quakes?
Can what? Sorry.
Can interferometry help detect
Yes.
Venus quakes?
Yes. Yes, so this is a good point, and that would be lovely because on Earth you would see these very clear patterns, right? Like the weird rainbow ones where you see how a quake moved. So theoretically, yes. I think probably most probable to do that would be Veritas, which has been confirmed to do repeat pass interferometry, and how it could detect very small scale surface changes. However, even though I think you have very distinct patterns of quakes that you could get in interferometry, you wouldn't be able to measure seismic waves directly, which was kind of what we were wanting to get at as well, since they usually contain a lot of information about the subsurface. So yeah, and you never truly do you truly know whether or not something would be seismic or aseismic? That's more of a theoretical, philosophical question, perhaps, but I find it interesting. So yeah, interferometry will definitely help, especially with surface changes, but it won't tell us anything about the seismic waves or the process of seismicity necessarily.
Great, thank you. There's one last question, as we have still a few minutes. And they ask, could Venus seismically be solely active due to volcanic activity, or might there also be subduction and abduction zones?
Yes, that's a very good question. So in the assumptions we did, obviously, in translating from like tectonic features on Earth to tectonic features on Venus, we did make the assumption that there is some kind of subduction on Venus associated with coronae. Whether or not that is true is, one of the things that the detection of seismicity would, either prove or disprove based on these estimates of what the amount of seismicity is we expect. So if there is subduction, and probably I would say that it is, only at the really biggest coronae like Artemis, where you could maybe have some kind of slab rollback type of feature that is, on Earth very much paired with seismicity. You would expect it there. Otherwise, maybe you're talking about mostly related to volcanism, or as Earth's intercontinental intraplate, oceanic intraplate, where you just have these isolated quakes every now and again that relieve stresses in the lithosphere without being necessarily associated with a plate boundary or a tectonic feature.